Welcome to Brain Vision.
Given the wave function, we start by taking its derivatives for the Schrodinger equation. So we take the first derivative, we substitute the wave function in, and we'll see that we have two terms since we have x multiplying an exponential. And we get the following result. Next, we take the second derivative, and from this, we're going to end up with more than two terms. We're going to have actually three. So the first term here is from the first term in the first derivative, but the second term in the first derivative gives us two terms. But we're actually going to be able to combine two terms in this second derivative. And when we do that, we get the following result. We actually get the -3 coefficient for those two terms. Now we just substitute into the Schrodinger equation. We have the -h bar squared over 2m multiplying this second derivative. -h bar squared over 2m will then multiply on two terms. And on the left-hand side of the Schrodinger equation, we then have three terms because the third term will be the potential multiplying the wave function. So we have the first two terms from the second derivative and the third term from the potential. This will then equal the right-hand side, which is the energy, times the wave function. And immediately we can start to cancel quite a few things. We see that the b's will cancel out. On the first term, we have the m, the mass cancels out. We have h bar squared canceling out in the second term. We see that we can combine x squared and x in the third term on the left-hand side, because notice you have an x cubed in the second term. This is going to be important in the next step. When we do this, we could rewrite to get the following for the next step. We get 3h bar omega for the first term times x times e to the minus negative m omega over 2h bar x squared. And then the second term becomes negative m omega squared times x cubed times the exponential function over 2. But notice that the potential term also becomes the same except with a positive sign. So those two actually cancel. So this greatly simplifies. And then, of course, the other side of the equation is still just the energy times x times the exponential function. So this shows us that the energy is just 3/2 times h bar omega. This is actually just the first excited state of the harmonic oscillator. So we continue on, and we notice that at x equals 0, since the wave function vanishes at x equals 0, well, psi is going to be 0. The wave function is 0, and that's because we have this x multiplying the exponential function. So the wave function is 0 at x equals 0. So now we take the first derivative to see where we can get a maximum value for the wave function. So we take this first derivative and we set it equal to 0 to get a maximum. And if you plot the wave function, you'll indeed see that these are maxima, not minima, that we're getting. That's always important to do when you're looking at extrema. Are you actually getting maxima or are you getting minima? And you can go back and check. And what we obtain is just a simple equation, because notice b goes away. It doesn't really help us in this equation. Also, the exponential function doesn't. So what remains is an equation that's a quadratic in x. And what it gives us then is 1 equals m omega over h bar times x squared, which can be rewritten as x equals plus or minus the square root of h bar over m omega. These are essentially the points where the wave function is a maximum, and this is essentially an amplitude equation, a value for x that's basically an amplitude. Now we can normalize the wave function as well. We can get a value for b. And when we do this, we just carry out the integral. We can just use a table of integrals, but you can always use polar coordinates to do this if you really wanted to evaluate the integral yourself. And because it's an even function that's symmetric about the vertical axis, the y-axis, you can, instead of integrating from minus infinity to positive infinity, you can multiply by 2 and integrate from 0 to positive infinity. So now, carrying out the integral, you get this. You get this result, and you see the 2's that cancel. And then finally you have the following multiplying together to equal 1, and this gives you b. And that further simplifies to all of this being under a 1/4 root. Basically, it's to the 1/4 power. So now we come to the potential, a consideration about the potential and about probability. So at these points under consideration, we see that the potential would actually exceed the total energy, which, if you recall, is 3/2 h bar omega, which is 1.5 h bar omega. That's the total energy, whereas the potential would be 2 h bar omega. So the classical probability would be 0. There's no way classically that the particle could have that much energy, although quantum mechanically it could. So the classical probability would be 0 then. That's how you would interpret that. Now, if we want the probability quantum mechanically, the way we would get that is at a particular point, there's no need to integrate. You would just simply take the probability density and multiply by the infinitesimal interval about that point. So if you know the size of your infinitesimal interval, namely delta, if that's what you're calling it, then this is how you would set this up. So let me get this to a point that makes sense to us in terms of the probability density. So up until, let me go back a little bit here. Up until here, we simply have the probability density. Oh, let me go to here. Up until here, we have the probability density squared. Right here. This is the probability density squared without multiplying by an interval. Now, we tack on the interval and multiply by it. 2 times delta over 2. This is the entire probability. It looks complicated, but it'll actually reduce. So we carry out some reduction, and notice that we have a square within an exponential right up here. So squared inside the exponential. That square is going to cancel with this square root inside of the exponential as well. And that's going to greatly simplify things inside of the exponential. So you also have a square root inside the exponential. You take those together and you get a lot of cancellation. So I actually chose to rewrite this so it wouldn't be so crammed there in the corner, but it's the same thing. And if we continue, then we'll go to the next line here, and we have some reduction that I've done. And when you do the reduction in the exponential, you simply get a -4 in the exponent. And everything else that starts to reduce will look like this. And then you can reduce that further. And your final result should look like this.